Okay, so then we will start with these antennas, and yeah, in some ways go back to the analysis of regular antenna elements, because now we have learned what's happened when we put them in an array configuration. But as I just mentioned, the first type of antenna, the Jagiuda, can be seen really as an array antenna. So what we will do to start is just to look at one concept of these antennas, and that is in an array, you've seen that you put two rather similar elements next to each other. So you can think that you have two dipole elements, like one there, you feed them, and then you say that this is an array, and we do an array factor, and we determine what happens. Now we change it slightly. So we say that the length are a little bit different of these antennas. So what we say is that we have one element, a driven element, and this element now has some specific length here. So it has a length L, and then next to that element we put another one. So here we just put a non-driven element. And that one has now a different length. So this one, we say it is L1 instead. Yeah, I don't know what's happened. Now my drawing disappeared from my setting here. I don't know why. Never mind. So we have two elements next to each other with slightly different length. And then we just see what happens with the radiation pattern when one of them is driven. And the first case you can see up here. So if you take a look at this one, there the element behind it, so the driven element is the element in the center here, that is driven in the center. So it's like a feed in the center of that element. And then the element behind, you can see it's slightly longer. So if you look down there, you can see it's not a big difference. It's a little bit longer. And then what happens with the radiation pattern, you can see it start to get a tendency to radiate in this direction. It still radiates in the backward direction, but it's pushing the radiation in the front direction. So that is something when we just put these elements close to each other, there is a mutual coupling between them. And the result of this mutual coupling is that they push the radiation in some ways in one direction. If we do the opposite version here, so we put now a shorter elements here instead in front of it. So if you see the length there, it's now slightly shorter. In reality now the element of this director here is now 0.46 lambda, the dipole 0.48. So it's very, very small difference. You can see the same effect here, that it's again pushing the radiation in the direction of this shorter element. So if we put a longer element behind, which is what we call a reflector here, it's push away the radiation from that one. We put a director, so a shorter element, and it's pushed the radiation in the same direction. And this is the basic principle of the Jagiuda antenna. Because in the Jagiuda antenna, this classical TV antenna, there we put a reflector behind the driven dipole, and we put directors in front of it. And it gives a lobe in the direction of these directors. And one way of thinking about how this happens and why it works is that you've seen that when we have elements of almost the same length, as we can see here, so these two, you can see the currents on them. You can see that you drive currents on the element in the center. You can see the colors are dark red or black in the center. That's the highest amplitude of the currents. But there is quite a lot of induced currents on this element and this element. And then you can see this is an array, because there are two elements next to each other. They both have currents. The currents radiate, so basically an array. And if you would like to control the direction of the radiation from this array, you should control the phase of it. And what you do by changing the length of the element is that you actually control the phase of it. And now an intuitive picture of why this works is that the driven element is self-resonant. And then by changing the length a little bit, you can make the element either capacitive or inductive. So if you think the dipole is just crossing through, so the reactance is 0. If you then change the length, you either move a little bit to the left or the right of that one. Then you make it either inductive and capacitive. And that's a change of the phase. So change the phase of this induced current. And by playing with this length, we can get the radiation going in the direction where we would like it to go. And that's what we've done in these ones. To do it in details, yeah, that we have to put it into a simulator and actually determine precisely what should the distance be between them and what should the length be of them. You can see in this example which has a length 0.1 lambda. But you can optimize over this to get a very good radiation patterns out of it. So what we have in all of these cases here is in some ways that we push the radiation towards the direction of the shorter elements and away from the longer elements. And this is really Yagi-Uda antenna. So combine this dipole with these elements where one is called reflector, and the other one are called directors. And in many cases, there is one reflector and many directors, but there can be different versions of these ones. So this is a Yagi-Uda antenna, and it used to be probably one of the most common antennas because it was so good, simple to build, very easy to put up on a rooftop and give good performance. And it was one of the first antennas that was ever manufactured or constructed that have this good property of a simple feed and giving good direction of the radiation. So fairly narrow beam width and pushing the radiation in the direction you would like it to go. So a typical picture of this Yagi-Uda antenna is what you can see down here. So here you can see two different Yagi-Uda antennas. In many cases, they are actually multi-resonant. So you put two Yagi-Uda antennas inside of each other. That happens in many cases. If we look at them, we can see a driven element. I know I pointed out this before. Here's a driven element, one driven element of this one. And it's typically a folded dipole. In many cases, it's a folded dipole. And in the back of it, you can see a rather long element that sits there. In the top version of these ones, you can see a different type of element, this more V shape. It's used in many cases of it too. And it's the same way, that's the reflector part. And then in front here, you can see many, many elements that sits there. So these are then pushing the radiation in these directions out here. So fairly narrow beam pushed in that direction of this antenna. So that is this Yagi-Uda. And here is then a drawing of it, a driven element here, slightly shorter directors in front of it. So wires with shorter length and a reflector behind of it, which has a longer length. That is the principles of the Yagi-Uda antenna. And this is an antenna that was developed in the 1920s, so 100 years ago, this year, basically. But it was not precisely 1920. The publications come a little bit later, but it was a development that took a few years starting around that time. And there is a reference here to that article, which is a reprint of the original article. And it's actually very interesting to take a look at, because you can see how much has changed. Of course, you were now doing your patch antenna, and it was not easy to design it. You built your patch antenna. It was not probably easy to build your patch antenna. I mean, it was a lot of work that you have to do. But imagine all the tools that you actually had to do it. Compare it if you went back to the 1920s where nothing of this existed. They didn't have an ECVNA to connect it to. They didn't exist. They couldn't make this, what to say, higher frequencies was very hard to actually get generators to produce. So they built large antennas. They couldn't simulate them. They actually built them, and then they had to measure, okay, which length is good? Okay, not so good. Try the next length, which means build a new antenna. And these are antennas of dimensions of meters. So it's a lot of manual work that has to go in and actually try this, but they found really good designs for them. Hard work in some ways. So you can press the link, you will come to an article. It's an interesting historical perspective that sits behind it. The name actually in this case have an interesting perspective too, because Uda did all the work and Yagi got famous for it in some ways. And for a long time, just called a Yagi antenna. But nowadays it's usually called a Yagi Uda antenna because Uda was actually the one who did basically all the work in designing these antennas. Okay, so if we then look at just some properties of it, we will see some of the components, what's happening with these cases. So this is the simplest case, or the simplest case of Yagi Uda antenna with only one director. So this is the element here, this is the director, and this is now the driven element as it's there. So we give a feed to that one, and this is a simulation, so put into the simulator, similar to FECO, this was CST, and just see what the performance are. And in these cases, you can see here that you have some S parameter, so you have some resonance frequency around there. So that's where your matching is sitting. And this is in this case around 2.75 gigahertz. And if you see the length that was used here, the driven elements in this case is 50 millimeters, and then a reflector of 55, director of 45. And you can compare them with the length. So we have here, what to say, a resonance frequency of 109 millimeters. So the elements are really this close to half a wavelength. But again, as the dipole, they are basically never exactly half a wavelength. They are approximately half a wavelength. The radiation pattern that we get out here, you can see out here. So again, you can see the geometry of the antenna sitting here. So this is the reflector. The middle one is the driven element and the director there. And you can see that the radiation is really shooting off in the direction of the director. So again, when you see this picture, you see them quite a lot in FECO. It's an overlay over two things. The geometry of the antenna is there to, of course, give a reference to it, but it's plotted in a completely different coordinate system as a radiation pattern. The radiation pattern is really this polar type plot, spherical coordinate system. So you can see it has an x-axis here, which is theta equal to 0. And then you have the spherical coordinate, where in some ways the distance from the center says what is the directivity of it, while the antenna is plotted in its own coordinate system. But they align in the way that we can actually understand them quite well. So we just have to interpret what these radiation patterns are. And the directivity of this case here is like 6.3. So it's an antenna where you can improve the directivity of your dipole. You can easily get up to directivity of 10 and so on by adding more elements in front of it. So very, very good practical type of antenna. When we then try to understand what happens there, of course, we can look at the induced currents because it is like an array that sits there. So the same picture as before here, this is the 2.75 gigahertz, where you really have this end fire mode of this Yagi Uda antenna. If you think about it as an array, is radiating along the direction of the Yagi Uda elements. And what you can see in these cases too here is that there are currents induced on all the elements. So the driven element here, of course, have the highest currents, but you can see that it's also inducing quite strong currents there and quite strong currents at the reflector. And of course, these are the one that works together to push the radiation in the direction forward to this Yagi Uda antenna. If we go to a lower frequency, so push this one down to 1.5 gigahertz. What happens in that case is that you still have a lot of currents on the driven element because you drive that element, so you force current into that element. But now the length of these ones here, these elements are really far away from lambda over 2. So these are non-resonant elements. And it means that basically on these cases, the current here is 0 and the current on that one is 0. So you don't really induce any strong currents on these two other elements. And then when you look at the radiation pattern, what do you see down there? You see you typically
it's like we have a dipole.
Yeah, because since you don't induce those ones, they don't radiate. And you get the radiation from the only element here in the center that has radiation. And this is a case, of course, a case where this doesn't work as an antenna. It's not working as the Yagi-Uda antenna should work. It works as like a dipole type antenna. So this is not what it's designed for. If we push up the frequency, the radiation pattern here can look in any strange way. Because when we go to higher frequencies, of course, we're leaving the simple resonances of these ones. Now at 4 gigahertz, it's more than half a wavelength. So it doesn't have a nice current distribution on it. You can still start inducing currents here because you can have higher order resonances of that one. And suddenly you see here, you got a radiation pattern that went straight up. So it's like in the broadside direction from this array. So it can go like in any direction. If I took another frequency, there will be another type of resonance frequency. So the Yagi-Uda is really this. It's very specific where it has to be used at this resonance frequency, where you have the element in resonance and you have the directors, the reflectors in the correct type of resonance and phase shifts. So you shoot the radiation in this direction. That is really the Yagi-Uda antenna. And there are rules of thumbs. So you can just go to internet or a book who says, this is the length of the director, this is the length of the reflector, this is the distance, and so on. So we can just look them up. So I'm not teaching them here. If you need them, you can find them. You can go to Feco. Now you have simulated your patch antenna. You have learned you can optimize in Feco. So of course, in a software like Feco, you can say, this is one length I should optimize over. I should optimize over this. I should optimize over this. And I should optimize over these distances. 5 parameters in this case. And you just ask Feco to do it. And it will do it very, very well. And you can then optimize for irradiation in this direction, and you could get a better results than the one I put up. So that is a very good way of, in some ways, designing these. And what's important for you to know is, of course, again, the basic principles. How would you do to design a Yagi-Uda antenna in these cases? How does it work? Okay, so that is our Yagi-Uda antenna. Before I go on to some very tiny Yagi-Uda antenna here, and speculative, any questions about this Yagi-Uda antenna? I think it is the one that, on every rooftop, sometimes not worked anymore, but they're basically sitting on top of rooftops. And the reason for, of course, they sit on the top of a rooftop is that they are simple to manufacture, they are cheap, and the wind doesn't blow them down. It's just a piece of wire there. It's not like a big surface. If you would have something that is larger as a surface, the wind will push it much higher. So these are very robust in some ways of using, and extremely good as an antenna. And when they came, they had a major impact of basically all the communication and broadcasting systems around the Earth. It really changed a lot of things when these were invented. Okay, any questions, comments? Why we use more than 3 antennas in the Yagi? You mean more directors in some ways? So what you can see here, you can see this has quite a few directors. So there are many elements. I do believe also these are multi-resonant, so there are actually 2 Yagi-Udas inside of it. So what you do is to increase the directivity more. So the one that I showed here, these are 3 elements. And you can see that the directivity here, if you look, this goes down to like 6.3. If you would like to have a beam that goes even more like this, that you can do by adding more elements in front. So you can make the beam more narrow and you make the directivity higher. And to do that, you add more elements. So think again back to arrays. What did we learn about arrays? Yes, by adding more elements, we got a more narrow beam. Same thing with the Yagi-Uda antenna. Of course, we cannot add hundreds of this because they will not couple very hard. After a while, the current is so low in them, so nothing happens. But you can definitely have like 5, 6, 7, and so on directors. And you will get a more narrow beam and higher directivity. So that's why you use more elements. And that's why sometimes in the back of it, you also see that you can have something larger on the back of it. You have a larger reflector. A little bit similar to the corner reflector. Okay, anything else about Yagi-Uda antenna? Take a look at the paper there. It's quite interesting. Very well written paper too. So, and 100 years old almost. Okay, so this, of course, Yagi-Uda antenna is a popular antenna. So one thing that has happened the last, say, around 10 years, maybe slightly more, is that there starts to be built antennas for many other frequency bands. So traditionally, antennas were built from some megahertz, gigahertz bands. That is where we had our microwaves. That's where we had all the broadcasting, wireless communication, and so on. And this is something we could manufacture because the antennas goes down to a few centimeter, decimeter in size. Maybe they go up to like 10th, 15th of meter or something. It's easy for humans to manufacture these things. The last, I would say, like 15, 20 years, the development in nanotechnology has really been, in some ways, exponential. So nowadays, people try to manufacture antennas for visible light and also like infrared radiation and so on. And in those cases, many things happens. And here is just one picture. I wouldn't say maybe it works as good as a Yagi-Uda antenna, but this is an attempt to make a Yagi-Uda antenna on a totally different scale in some ways. So when you look at the length scales here, this is 200 nanometers. So basically nothing. You can see that the elements here, the reflector, the directors, they are very thick. They are not like a thin wire that we think we have. And that's of course because it's very hard to make something so small. You come down to the what to say, the material properties really comes in, the individual atoms and so on start to come in at these scales. So you start changing it. You cannot build a coaxial cable or twin wire LED that feeds this, but you can put other things. You could put molecules, so there's quantum dots that actually generates radiation, and then you would like to focus the radiation in one direction. This is some artist illustration, what they think it should look, so you can see the light should go in one way. In reality, no, it doesn't really do that from this structure, but it's an attempt to do it, and there's a lot of effort to actually put up these sub-wavelength structures that interact a lot with the electromagnetic field to optical light in some ways. So this is manufactured for 800 nanometers. A completely different scale. But again, what have we learned with antennas? It's not the frequency that's interesting, it is the wavelengths. So if we have 800 nanometers, yeah, we have to have a structure that is on a similar scale in some ways. If it was a pure good metal here, yeah, we could make it half a wavelength in these cases. And here we can see that they are not really half a wavelength. And that's because metals at optical frequencies don't behave as metals at microwaves. They behave completely differently. So metals are not really good conductors at optical frequencies. And they're changing all the design rules for these things. Of course, there's challenging with manufacturing because they're so small. Imagine you did your own patch antenna this week. You could sit there with a pair of scissors and you could pretty cut it in the size you would like to. How do you do that when it should be 200 nanometers? You cannot do that with a pair of scissors. So manufacturing is of course much harder. But there is a lot of potential use of this because these can then be used for other things than, for example, wireless communication. So solar cells, this gets popular in sensors, nano tweezers, where you can touch individual atoms and molecules and so on. There's a lot of work going on in this kind of directions. And Yagi-Uda antenna shows up there. The materials is the hard thing, and I will come back to that actually a little bit later in the course. As I mentioned here, that these are not really good conductors. And conductors, we would in some ways measure that, say that there is a conductivity or resistivity that has a good, what to say, property. It's a conductivity that's very high. And if we look here at the conductivity of a typical, let's say, materials in these cases, so we can look at these ones here. This is conductivity. And it's just estimated from these parameters. You can see here when you look at the wavelengths in these scales, when we sit in our world, we typically is over here. You can see that the conductivity is constant. It does not depend on the wavelengths. When you go to optical frequencies, you are sitting down here. That is the range where you basically are at optical frequencies. So one thing you can see is that the conductivity is much lower. Here it is like 10 to the power of 7, 10 to the power of 8. Down here, orders of magnitude lower. So it doesn't really conduct in a good way. And you can also see that it depends a lot on different frequencies here. So that is called dispersion or temporal dispersion. The material parameters are frequency dependent. And that kills one of the principles that I've taught you in this course, that when you look at antennas, you don't have to care about the specific wavelengths or specific frequency. You just compare the size of your antenna with the wavelengths. So we measure the dipole in half a wavelength dipole. We say how long is it compared to the wavelengths. That doesn't work anymore when we go to these optical kind of structures, because dispersion is so strong. The dependence of these materials on the frequency is too high to do that in some ways. So that starts changing a lot of things in the design. We will come back actually a little bit to this, not much, but a little bit. Okay, so that was the Jagiuda antenna. Now we will go back to another antenna that we have looked at once. We looked at the spiral antenna, and we will now do this from, first of all, the other perspective of spiral antenna, but we will do it from something that's called Ramsey's principle. And it's one of those principles to understand very wideband antennas. Why is an antenna broadband, meaning it could work from like 1 gigahertz to 20 gigahertz? What is we would demand from that antenna? And something here that's called this Ramsey's principle is that the impedance and radiation properties up here, they are frequency independent if the antenna shape is specified only in terms of angles. So what does that mean? It means there does not exist any length scale. If there's only angles to describe this structure, in that case, there is nothing that can say how long is it. And if there is no length scale, we cannot say it is half a wavelength, it's quarter of a wavelength, it's 2 wavelengths. It doesn't exist, that scale. And actually, if you have that property, your antenna parameters here, like the impedance, they are not depending on frequency because they don't depend on the wavelengths. And that means you basically have infinite bandwidth. So in these cases, you have no length scale, so equally good for all wavelengths. It also requires that it has an infinite size. So maybe not the most practical stuff, but of course we then do approximations of them. And the finite versions of this, so finite dimensional versions, are very good approximations of this. And the typical cases here are the spiral antennas. We have looked at once before in the course. We have looked at self-complementary antennas. And some antenna we will look at here, which is similar to Jagiuda antenna, which is called log periodic antenna. It looks a little bit similar. The principles are very different. So if we take a look at these ones, and we start with this self-complementary antenna. So this spiral antenna here to the left is self-complementary. And what means with that is, again, that I have metal here, I have air here. So if I take this picture and I change white to gray, I basically get the same geometry again. I don't change it. I might turn it and so on, but I don't really change the properties of it. That means it's self-complementary. And if you have an antenna that is self-complementary, your input impedance is half of the free space impedance, basically 190 ohms. So of course, if you then build a wire that is 190 ohms or 189 ohms, it's perfectly matched for all frequencies. Incredibly good. So this is one of the principles that can give this. And of course, again, it has an infinite size. So there will always be a finite approximation of it. And close to the feed, you also have finite dimensions. So those will set the highest frequency and the lowest frequency that you can use. And in reality, we take finite versions then as approximations for these ones. And we have actually already looked at these two antennas that has this self-complementary property. So similar as we shown before, this is the spiral antenna. I showed it before when we had this broadband antennas, or we looked at the spiral antennas. It is one of the circular polarized antennas. And you can see here you have the reflection coefficients of S11. And if you look here at like 0.3 or something, you can see it's really matched from this frequency up to some frequency over here. So very wide band, and you can make those even more broadband if you would like to. So you can make this really broadband. But as we explained when we talked about the spiral antennas, they have a problem that they radiate up and down. So they're hard to attach to something. The lowest frequency where this works can be attached to the resonance here of one loop. So basically it has that making this loop resonance. The circumference of these ones is in some ways the lowest frequency where you can use it. And then if you go to higher frequency of these ones, you can find in some ways a loop that sits here, and you can make that resonant and so on. And that's why you create so many resonances on this one. So in some ways there are almost no resonances. It's just broad. So that is one broadband type antenna.
Can I ask a question?
Yeah.
Can you go back a slide?
Yeah.
What is the A variable on the spiral scheme?
Yes. So maybe I should mention this one. That is the radius here. So this distance is called A.
Thank you.
So that is the radius where it sits. And that means that Ka in some ways is the same way as to measure the circumference of these ones in wavelengths. So if Ka here is equal to 1, it's the same thing that the distance around this is 1 wavelength. That is the same scale. We talked about that when we talked about the spiral antenna. Okay, so another of these antennas that has this very broadband properties, and on a first view, it could think about it looks a little bit like Jagge-Uda, but it's very different from Jagge-Uda. It's the log periodic antenna. So here is one picture of a log periodic antenna, and here is another picture in real life in some ways. And what you can think about with the log periodic antenna is that you have the dipole. You know that you can make the dipole resonant by changing its length. So why not just put a lot of dipoles next to each other? And that's very similar what you do in the log periodic one, because you can see here is a very long dipole. So that could basically be your lowest frequency, your longest wavelength is half of that one. Yeah, it's resonant. Go to higher frequency, and maybe this one is resonant. Go to an even higher one, then this one is resonant. And that means that you can drive this antenna at a lot of different frequencies, because somewhere there is like a dipole that is close to resonance. That's an intuitive picture of why this works. It also have the properties of this description of angles in some ways. So there is a log periodic one. You have a specific, what do you say, dependence here of the distance and the length of these ones. So in some ways you only have one parameter alpha here, which is the quotient with the different spacings. You can see there is a spacing here, there is a different spacing, here and so on. And the lengths that sits here, so these ones here, that's of course then the length of different elements. So they are always changing a little bit when you go from one to the other. And if you do that, you get what's called a log periodic antenna. So that's basically its definition of making it log periodic antenna. And in principle, you can think about it as different dipole that's resonant. It's an antenna that is not really have a radiation pattern as a pure dipole. So if you think it's only one of these that's resonant, it will really be, a pure dipole pattern like a donut, but it's not. It's a pattern that is more similar to those Jagge-Uda antenna with 3 elements. So it actually have a directivity in some ways. It does radiate in one direction. But now we could think about one thing with this one. So, okay, it's broadband. What is then a problem with it? If you think you would send, for example, a pulse through this antenna, it's matched for all frequencies. But it would mean that the lower frequencies of your pulse are transmitted from this position. The higher frequencies of your pulse, shorter wavelengths, are sent from this position. So actually they are sent from different parts of the antenna. And that is something that in antenna terms are said that the phase center is moving with frequency. So they don't have a stable reference point. The phase of the antenna is, in some ways, the center of the antenna is moving with frequency. And that means if you send a pulse of this one, you don't get a pulse out. You get something else that comes out of this one. I get a question here on the chat that alpha is greater than 1. And yes, we could say it's greater than 1. It depends on how we order this in n. We could also say it's less than 1. It doesn't really matter. So it depends if we say that this is the first element, this is the second element. So if we go in this direction or this direction, then we can just take 1 over this one to get the new alpha. So it depends on what order we have ordered all of these distances and the lengths. Okay, so this is an antenna that in that case would disturb the radiation pattern. If we look at the measurement for it, you can see the properties down here. So you can again see that it's fairly well matched here, depending on what the threshold level you take. And if you start with the lower frequencies, you can see this one goes from 0.5 gigahertz, at least up to around 8 gigahertz. So very wide band, and that you can easily get out of this type of antennas. Large bandwidths is easy to get out. Okay, so let's look at more types of broadband antennas. And if we think about these things with this dispersion, that is a problem if you would like to transmit the pulse, then you can start changing the shapes of these ones. And what you need to in some ways make a nice transition of the wave, think almost like in acoustics when you have like a horn that you're blowing in. Next week we'll talk about horn antennas. So you have a signal that comes from like below here or here. So in some ways you feed the signal out. And what you would like it to do is just to continue to radiate straight up here. That's what you would like to do. And that means you can make it gradually wider and wider. You can have like some tapered horn that goes up. This is called here a butterfly antenna, of probably the one who made it. I think this one looks like a butterfly. And you can again see here that matching is pretty good. Again, wide bandwidth. So in some ways, it's not actually very hard to get out this wide bandwidth as long as your antenna is fairly large. It needs to be on the size of like a wavelength or larger at the lowest frequency, but not much more. Then you can get enormous bandwidth out of this type of antennas. And here you have like this transition zone where you just make it smooth. And again, you can see radiation patterns basically sticking straight out here. So fairly nice radiation patterns. And again, both this smoothness here, what it does is that it's make it more wideband, less oscillations, but it also reduces the side lobe levels. If it's hard corners, it will also make the radiation go in different angles, which would increase the side lobe levels. And this is a similar one. It's just a different feed in some way. So the first one was idealized. This is a coaxial cable feed, and it creates a little bit of a problem in the design of this one. But these are antennas then that has less dispersion, but they are still very broadband. And if we look at what this dispersion is, so we can see one antenna here, lens antennas, we will also talk about next week. So here you can see something that it looks almost inspired by optics. You put a lens in front of your antenna, and optics, yeah, that is actually electromagnetic waves. So if you have a lens there, then you can put a lens on antennas. And it's very popular for some cases to do that. And if you would do this now in radiation with just over a cable, let's say you transmit a pulse. So this is time in nanoseconds. So this is a short pulse. So let's say you want to propagate this pulse train over air instead. If you do it with a horn antenna, what you get out is something that looks like this. So you can see that you destroy the shape of it. That is the dispersion. And that's because the horn antenna is dispersive in the same way as the log periodic antenna. A lens antenna here, you see, can do this with the same type of structure that sits there. So you can push down this dispersion. You can remove the dispersion of this. So it's broadband, but it also have a fixed center of radiation. Radiation center is fixed for this one. And this is a 60 gigahertz antenna. And here you would have a 20 gigahertz bandwidth for this one. So enormous bandwidth. If you think about communication, of course, everybody would dream about having 20 gigahertz bandwidth. And usually it's not free, that spectrum. But of course, there can be other frequency ranges where we actually can do stuff with these very large bandwidths. And in ultra wideband communication, there you try to go around the regulation with spectrum by actually sending pulses where you lower the power so low, so you're below the levels, and you can actually transmit almost on any frequency. So the idea is that to do ultra wideband communication systems for that. So now the first hour is gone, and I'm just talked a little bit about different type of antennas. So back to the old antennas here, the Jaguda, log periodic, and so on. And then after the break, we will really go into the part that you will do next week, which are these measurements in some ways. So I will just have a different Beamer presentation for that, and we will go through what you actually, or what to say, we'll go through the theory that you need to do the lab next week, because then you're going to measure on your own antenna. And I hope you have seen that the sign up for the labs next week are open. So you can go to the Canvas page and you can sign up for hours to do the third lab and actually measure your patch antenna. So with that, questions? Okay, if there are no questions, I will stop the recording.